So quantum mechanics is a very strange theory. Nothing you've studied about in classical physics, nothing in the experience you have with the physical world can prepare you for it. It's just the case that at the level of elementary particles, nature behaves in a very strange way. And this strange way is described by this theory called quantum mechanics. In fact, this theory is so strange that Feynman once said, nobody understands quantum mechanics. By which he meant not that nobody understands it, but nobody intuitively understands why it behaves, nature behaves the way it does at the quantum level. Okay, so let me describe some of these funny aspects of quantum mechanics. So the first aspect of quantum mechanics that's strange is that it's inherently probabilistic. You know, when you measure something about an elementary particle, the result is always a sample from a probability distribution. It's not a determined quantity. You know, it's you only get probabilistic information about the system. A second aspect of quantum mechanics, which is bizarre, is that you cannot make a measurement of a system without disturbing it. And then there are many other funny aspects of quantum mechanics. So elementary particles like electrons and photons behave like nothing at all that you're used to in the classical world. So they behave neither like particles nor like waves, even though they share some of the features of each of them, but they don't behave like either of these two entities. What's interesting though is that, you know, all these particles, so photons, electrons, etc., they all behave in the same way, not like particles, not like waves, but like something else, and it's always the same something. So in this lecture, in the rest of the lecture, I'll describe a particular experiment called the double slit experiment, which highlights both the commonality as well as the differences between the behavior of quantum particle, you know, quantum entities like electrons, photons on the one hand, and particles and waves on the other hand. So we'll be able to see in what sense quantum mechanics gives us particle-like behavior, in what sense it gives us wave-like behavior, and in what sense it deviates from both of these. Now this experiment, the double slit experiment, is a very basic experiment, and it illustrates many of the fundamental features of quantum mechanics. So it's, you know, even though we won't directly rely on this experiment for anything that follows, it'll actually help you a lot if you try to understand this experiment for what follows. On the other hand, you know, for some of you, if it doesn't make any sense, that's okay. Because, as I said, we won't rely on it. And starting in the next lecture, I'll start by describing qubits or quantum bits. And we'll do an entirely self-contained exploration of basic quantum mechanics in terms of quantum bits. Okay. One other thing, for those of you who have trouble, you know, intuitively grasping this double slit experiment, it would still be useful if a week or two from now, once we have, you know, once you actually understand the basics about quantum bits, it would be worthwhile if you come back and review this lecture and see if the double slit experiment makes more sense at that point. Okay, so let's get started. Okay, in the double slit experiment, we have a source of, you know, of either light, form of photons or electrons, and then there's a screen with a single small slit in it through which these electrons or photons have to pass. And then at some distance from it, which I guess I've shrunk to make it all fit, there's another screen with two slits carved into it. We'll label these slits slit 1 and slit 2. And then a long way from there, there's another screen, which is where we are going to detect where these electrons or photons ended up. So now what we are going to do is, later I'll describe to you how this experiment, what the outcome really does look like if your source actually was shooting out electrons. But first, let's imagine, let's try to understand what the behavior of this experiment would be if the source was shooting classical particles, which we'll model as bullets. So let's think of this source as a machine gun, which is firing bullets. Bullets, because they are discrete objects, they are indestructible. We'll think of them as discrete, indestructible objects. And so this plate then becomes an armor plate with a hole in it. And the detector is just a sandbox, which we place at a distance x from some fixed reference point. We'll also assume that this machine gun is sort of jiggly. It's not held very, very firm, so that the bullets sort of spray at, along different trajectories. And moreover, I'll assume that this slit here is narrow enough that the bullets actually tend to strike the edge and spray off the edge, so that the trajectory of the bullet, if the bullets happen to go through this hole, they actually spray according to some angle out here. And then some of these bullets then make it to one of these slits, slit 1 or slit 2, and once again they end up, they actually end up ricocheting off the edges and going along some random path. So now, of course, you can keep the machine gun firing and at some rate, and you can see how many bullets end up at this detector at location X. And of course, this is going to be a random variable because, as we said, the bullets ricochet off at random angles. So you can only talk about how many bullets end up in this detector over a certain period of time, let's say over a period of a minute. And let's say that on average at X, you have some number of bullets, let's say 3 per minute. So we'll think of that as the average rate at which bullets end up at X. Now, of course, this 3 does not have to be a natural number, a whole number. It can also be some number like 3.5 or 3.1. And what that means is, on average, in the course of a minute, you get 3.1 bullets. Meaning, if you actually did the measurement over a period of 10 minutes and you got 31 bullets during that time, you would say that the rate at which bullets are ending up in this detector is 3.1 per minute. And so now you can plot how many bullets end up in this detector as a function of X. And you might get some curve like this. So it might have two humps in it, two peaks corresponding, let's say, to straight line paths going through slit 1 or slit 2, and it falls off on either end. Now you can also close one of these slits and ask how many bullets end up if you only have slit 1 open, or how many end up if you only have slit 2 open, and you get these two different curves like this. And so if we label this curve as n1 of X and this curve as n2 of X, right? That's the curve. Then when both slit 1 and slit 2 are open, we get this curve n12, and the equation that it satisfies is that n12 is equal to n1 plus n2. So the number of bullets that end up at X, if both slits are open, is the number that ends up if only slit 1 was open, plus the number if only slit 2 was open. It makes a lot of sense. That's very simple. So now let's repeat this experiment, and now let's let's imagine that we are doing this experiment with water waves, with waves. So what we have is a little pond. The source is some vibrating object which sets up these little waves. And let's say the vibrating object is vibrating at a fixed frequency so that the waves are nice and steady. And you have some sort of a barrier here with a little slit through it so that as the wave gets through this little slit, it starts spreading, and then it spreads all the way till it gets to this second barrier with the two slits, and again the wave starts spreading through the two slits. And now our detector is just going to detect what's the intensity of the disturbance at the point X. What's the energy of the wave at the point X? So one way to measure it is by putting some object like a cork in the water, and you see how vigorously it gets disturbed. What's the energy of the cork? And that's what we're going to measure. And so when we measure it as a function of X, that intensity, which let's say we call that I sub 1, 2, so denoting the fact that as a function of X, denoting the fact that both slits 1 and slit 2 are open, it follows this very funny curve which you'll probably recognize from maybe high school physics as the interference pattern. Okay, so what happens in this interference pattern? So remember, we said that we have a wave coming through each of the two slits. And now if you look at the point right in the middle here, where you have this crest, this big crest, right? So what happens at this point in the detector? Well, what happens is, since it's equidistant from both the slits, and since the two waves from the two slits are completely in sync, crests from both the waves appear simultaneously here because they have an equal distance to travel from here to here. And troughs appear also simultaneously, so that you have constructive interference between the crests and constructive interference between the troughs. And so the crests become higher and the troughs become lower. And so the energy of this, the disturbance here is really much higher. The waves reinforce each other. On the other hand, if you move a little further away from the center, then about the time the jth crest arrives from slit 2 is the time that the j minus first trough arrives from slit 1, because they're off by exactly half a wavelength. And so they more or less cancel each other out. Perhaps the wave from slit 1 is a little bit stronger than the one from slit 2 here. And so they don't quite cancel out, but they very nearly cancel out. And so you get nearly completely destructive interference, and the water is essentially close to being still. And so the cork is imparted almost no energy at all. And similarly, if you move a little further, then again you get constructive interference here, because now when the fourth crest arrives from slit 2, it's at the same time that the third crest arrives from slit 1, and you get constructive interference again. Okay, so that accounts for this sort of this sort of pattern. On the other hand, if you were to open only slit 1 and ask what's the intensity as a function of X, you get this this curve that we saw with bullets, I1 of X, and with slit 2 you get this curve I2 of X, and I1 2 of X is not equal to I1 of X plus I2 of x. Okay, so how do you get I12 from I1 and I2? Well, it's actually very simple. So the intensity at x, the intensity or the energy of the wave is just the square, is proportional to the square of the height of the wave. And so what you have is that the height, when both slits are open, is exactly equal to the height when only the first slit is open, plus the height when the second slit is open. But of course, what this means is that I12 of x, which is h12 of x whole thing squared, is not equal to h1 of x squared plus h2 of x squared. In particular, if h1 is very nearly equal to minus h2, then h12 is 0, very close to 0. So I12 is very close to 0, even though I1 and I2 are each not close to 0. Okay, so that's the case with waves.